name's Joe Calantoni, and I work at the U.S. Naval Research Laboratory at the Stennis Space Center Detachment. And I'm here today to talk to you about some work that we do in the sediment dynamics section. I'm a research physicist by training. I'm also the head of the sediment dynamics section. We're a group of scientists and engineers who are focused on seafloor, estuarine, and riverine bottom problems for the Navy. You might wonder, why does the Navy care about sand and mud? Well, it's really important for making forecasts of the environment. It's also very important for understanding how we communicate in the underwater environment. And it's critical for finding unexploded or potential hazardous targets, we call them today, that may be lurking on the seafloor, and we'll talk about that in a second. So I'm going to show you a little video. Here we have a quad pod is what we call it. And so this is an underwater instrument platform, and you can hear some acoustic noise happening in the background here. And so here's a sector scanning sonar that you just saw. We're going to talk about that data in a minute. Up here, this is a acoustic Doppler Profiler. So this looks up to the sea surface. It gives us waves and currents in the water column, and that records at 2 hertz. And so that means we get 2 hits of the wave height every second. Now the diver is swinging around, and so this is kind of a massive structure. It weighs almost 2,000 pounds when it's sitting on the deck of a ship. You see divers working down here. Here's another high-resolution profiler to give us velocities near the bed at very high resolution. This is an acoustic Doppler velocimeter. This is for measuring turbulence. I want you to take note at how close this is to the bed. It's hovering about 6 inches above the bottom, and later we'll show you a picture of what happens to it during the experiment. These are some optical backscatters, and these are courtesy of our colleagues at the University of Florida that we work with. And so here you see divers. This is a target field, so these are surrogates of unexploded ordnance, and this is part of a project that we're doing for the Strategic Environmental Research and Development Program. And so what I'll show you next is the data that we got from the quad pod sitting down there on the seafloor. And so you might be wondering why we're putting things that look like bombs on the seafloor and trying to understand what their phenomenology is. Well, CERTA is tasked with coming up with the science to help managers, site managers, remediate and manage their contaminated sites. And there are over 10 million acres of contaminated underwater environments in the continental U.S. and in our territories. And this is a very strong environmental problem that we have to deal with. So our task here is to try to understand what these things do when the waves get big, and I'll show you exactly what happens. So here we got 3 different panels for you. This is the wave height up in the top. This is the interesting panel. Here's our sonar imagery. These are 155 millimeter howitzer replicas. These are 81 millimeter mortar replicas. And this is a very low density 81 millimeter mortar. And so I want you to watch that one. And that thing is plastic, and it just takes off. And so one of the things that we hypothesize is that the behavior of these munitions is highly dependent on the density of the munitions. These howitzers, the real things weigh about 100 pounds when they're sitting on the deck of the ship. And submerged, they weigh almost 50 pounds in water. And so you notice we get beautiful sand ripples that form. And now here we're going to highlight a storm event that occurred between 4 and 7 May in 2013. And this was in the northern Gulf of Mexico. And so now I've slowed down the video for you, and watch these large targets. They're going to rotate first, and then they're going to roll offshore. So the shoreline is nominally right here. And then afterwards, during the downslope of the wave activity, the targets are buried completely due to sediment transport activity. You notice now the ripples have started to reform in a different direction. So let's look at this one more time. And on this next play, I'm going to highlight one of the 81 millimeter mortars. The very bright spot there are the fins on the 81 millimeter mortar. And this thing is not able to rotate like the larger ones are. The fins lock it in place, and it just kind of gets dragged along the seafloor a little bit before the sand wave comes in and buries all the target field. Notice one of our 155 tips there just slowly disappearing in the image. Now, this ends on May 8th here, the morning of May 8th, and we did dive operations to do maintenance. And here's what you see. Remember that ADV I showed you? Well, here it is, half buried in the seafloor. And that target that we saw, that 155, notice the sand ripple crest here. And here's our big 155. So this thing is about this big, you know, to give you the scale of it. So the divers went down afterwards and they reset these targets. And what you see is you get a little bit of a wave blip here, and it resets the ripple field. and afterwards the waves decay. And so this is also kind of an interesting data set because now we get to see the effects of biology. Fish come in and they start feeding on the seafloor. You see these little pock marks that pop up. Those are fish feeding. And so fish in the northern Gulf of Mexico are a major diffuser of seafloor roughness. And why do we care about seafloor roughness? Well, because seafloor roughness is a very important boundary condition to how the Navy communicates underwater. So these are the kind of interesting problems that we're doing at the U.S. Naval Research Laboratory at Stennis Space Center. My name is Joe Calantoni, and I hope you enjoyed this video.